Did you know that the material you choose for 3D printing can mean the difference between a part that lasts decades and one that crumbles in your hands the first time you use it? Most people think additive manufacturing is all about the machine, but the real secret is what you put inside it. Welcome back. Today we are diving deep into AM materials, the powders, filaments, resins, and metals that make additive manufacturing actually work. By the end of this video, you will understand the main material categories used in 3D printing, why material properties matter so much, how materials behave differently depending on the process, what makes a material printable in the first place, and where material innovation is heading next. This is the foundation that separates someone who just operates a printer from someone who truly understands the technology. Let's get into it. Section 1. The material families. There are 4 main families of materials in additive manufacturing: polymers, metals, ceramics, and composites. Think of these as the 4 kingdoms of AM materials, each with its own rules, strengths, and weaknesses. Polymers are by far the most common. When you picture a desktop 3D printer cranking out a plastic prototype, that is a polymer at work. They are lightweight, relatively cheap, and easy to process. You've got thermoplastics like PLA and nylon, which melt and resolidify, and photopolymers, which harden when exposed to light. Metals are where things get exciting for industrial applications. Titanium, stainless steel, aluminum alloys, and nickel superalloys can all be printed today. Metal AM parts are showing up in aerospace engines, medical implants, and high-performance automotive components. They are strong, precise, and increasingly cost-competitive for complex geometries. Ceramics are the quiet achievers. They handle extreme heat better than most metals, resist chemical attack, and show up in applications like dental crowns, cutting tools, and electronic components. Processing ceramics is notoriously tricky, which is why they are less common, but the field is advancing fast. Composites blend 2 or more materials together, often a polymer matrix reinforced with carbon fiber or glass fiber, giving you properties that neither material could deliver alone. Now here is the question that should already be forming in your mind. If we have all these options, how do engineers actually choose the right one? That is coming up next. Section 2. Material properties that matter. Choosing a material is not just about picking something strong. It is about matching a material's properties to the demands of the application. Let us walk through the properties that engineers care about most. Mechanical properties top the list. Tensile strength tells you how much pulling force a material can handle before it breaks. Hardness measures resistance to scratching or denting. Ductility tells you how much a material can deform before it fails. A hip implant needs different mechanical properties than a turbine blade, even if both are made from metal. Thermal properties matter enormously. A material might be perfectly strong at room temperature, but soften or warp under heat. This is especially critical for polymer parts used near engines or electronics. Melting point, thermal conductivity, and heat deflection temperature all come into play. Then there are surface properties: how smooth or rough the final surface is, how well it bonds with coatings, and whether it is biocompatible for medical use. A dental implant sitting inside someone's body has to meet completely different surface requirements than a bracket on a race car. What is fascinating is that the same material can have dramatically different properties depending on how it was printed. The direction of printing, the layer thickness, even the temperature inside the build chamber, all of these influence the final mechanical performance. Which raises an interesting question. If process affects properties so deeply, what exactly happens to a material during the printing process? That is exactly what we cover next. Section 3. How materials behave during printing. Every AM process puts a material through a specific kind of stress. Understanding that stress is key to predicting how a part will perform. In powder bed fusion processes, like selective laser sintering or direct metal laser sintering, a laser rapidly heats and melts tiny particles of material. Then they cool and solidify layer by layer. This fast heating and cooling cycle creates something called residual stress, essentially tension locked inside the part. Without careful control, parts can warp, crack, or distort. In fused deposition modeling, thermoplastic filament is melted and deposited line by line. The bonds between layers are often weaker than the material within a single layer. This is called anisotropy. The property varies depending on direction. A part printed vertically may be significantly weaker along the z-axis than along x or y. Resin-based processes like stereolithography cure photopolymers with UV light. These materials can be very accurate and detailed, but they are often brittle compared to thermoplastics and can degrade over time when exposed to sunlight. Metal binder jetting deposits a binder between metal powder particles, and then the part is sintered in a furnace. During sintering, the part actually shrinks, sometimes by 15 to 20%, which engineers have to account for in their design. All of this means that the material and the process are inseparable. You cannot choose one without thinking about the other. So what makes a material actually suitable for printing in the first place? Section 4. Printability and processing requirements. Not every material can simply be loaded into a printer and processed. Printability is a real engineering consideration with specific requirements. For polymer filaments, viscosity at processing temperature matters enormously. The material has to flow smoothly through a nozzle without clogging, but also hold its shape immediately after deposition. Moisture content matters too. Many nylon-based materials absorb humidity from the air, which causes bubbling and poor surface quality during printing. For metal powders, particle size and shape are critical. Powders need to flow freely and pack uniformly into the powder bed. Particles that are too large produce rough surfaces. Particles that are too irregular do not spread evenly. Metal powders also have to be handled carefully because fine metal particles can be explosive or toxic. For photopolymers, the chemistry of the resin determines how quickly it cures, how deeply the light penetrates, and what mechanical properties develop. Engineers tune these formulations carefully to balance cure speed, accuracy, and final strength. Post-processing is another layer of the story. Many AM parts are not truly finished when they leave the printer. Heat treatment relieves residual stress in metals. Support structures get removed. Surfaces get polished, coated, or infiltrated with other materials. The material has to tolerate all of these steps without degrading. This brings us to the most exciting part of the entire topic. Where are AM materials actually heading? Section 5. The future of AM materials. The materials landscape in additive manufacturing is moving fast, and the directions being pursued right now are genuinely exciting. Functionally graded materials allow engineers to print a single part where the composition gradually changes from one region to another. Imagine a turbine blade that transitions from a tough metallic core to a ceramic outer surface, exactly the properties you want in exactly the right places. Multi-material printing is enabling parts with embedded electrical conductors, flexible joints combined with rigid structures, and even biological scaffolds for tissue engineering. Medical researchers are printing structures seeded with living cells, aiming eventually to produce functional human tissue. High-performance thermoplastics like PEEK and Ultem are expanding the polymer envelope, offering heat resistance and strength that rival some metals. These materials are already being qualified for aerospace and implantable medical applications. Sustainable materials are gaining serious attention. Researchers are developing bio-based polymers, recycled powder systems, and processes that dramatically reduce waste, addressing one of the biggest criticisms of industrial manufacturing. Here is the big takeaway. In additive manufacturing, the machine is just a tool. The material is where the real engineering happens. Understanding material families, properties, process interactions, printability, and future directions gives you a complete picture of why AM is transforming industries from aerospace to medicine. If this video helped you connect the dots, please hit that like button right now. It genuinely helps this channel reach more students and engineers who need this content. Subscribe so you do not miss the next deep dive in this series. And drop a comment below with one material or application you want to learn more about. I read every single one and it shapes what I make next. See you in the next video.